Hey guys, Mr. Backerberg here. In this video, we're going to take a look at transformations of trig graphs. So a general sine function, also called a sinusoid, can be written in the form f of x equals a times the sine of b times x minus c plus d, and each one of those values, a, b, c, and d, affect the picture of your graph and your function in a different way. So as far as that a value, the absolute value of a is the amplitude, which helps describe the height and depth of your waves. For that b value, that affects the period of your function, and to find the period, we take the absolute value of 2 pi divided by the b value. C is going to be a horizontal shift, either left or right, depending on what that C value is. Remember, horizontal shifts are backwards of the way that we would think they would be. So minus actually moves you to the right by a specific amount, and plus would move you to the left by that same amount. And then that D value on the end is a vertical shift, and those always work the way that you would want them to. Plus moves you up a certain number of spaces, minus moves you down that same number of spaces. Now, all of this same exact information will hold true for cosine functions as well. So it's not just sines, but also cosines. So in this example, we're going to look at transforming a trig function. So we've got the function y equals 3 cosine of 2x minus pi plus 1, and we want to figure out some things about it. We want to figure out its amplitude, its period, the domain, and the range of this function. So as far as the amplitude goes, that's the absolute value of a, which we find at the very beginning of the function. That's your constant multiplier out in the front. So it's going to be the absolute value of 3, which is just 3. Now, as far as what the amplitude means, that means that the waves of our graph would have a height of 3 units away from the midline. Now, as far as finding the period, that's the absolute value of 2 pi divided by b. Now, this function isn't quite written how our previous one was. I'm going to adjust it just slightly. And what I'm going to do, we've got this 2 happening in front of the x. I'm actually going to factor that 2 out of here. Now, factoring works like dividing, so to factor that 2 out, I'm going to have to divide both of these by 2. So that's going to leave me with x minus pi over 2 inside of my parentheses, and then I still have that plus 1 on the end. So my b value in this case is 2. So it's going to be the absolute value of 2 pi divided by 2. Those 2's cancel out, so we just get the absolute value of pi, which is just pi. So this function would have a period of just pi. Now, as far as the domain deals with the x values that are safe to plug in. In general, sine and cosine graphs have a domain of all real numbers. So this domain would run from negative infinity up to positive infinity. And then our last thing is the range of our function. So I'm going to look at 2 pieces here to help me determine the range. Typically, with a sine and a cosine graph, it would bounce between -1 and +1. But changing the amplitude changes the height of those waves. So having an amplitude of 3 would typically mean that our graph is going to be bouncing between -3 and +3. But there's one other thing that we have to take into account, and that's that +1 on the end. So along with having that amplitude of 3, we're also shifting this graph up 1 space. So instead of bouncing between -3 and +3, if we shift those up 1 space, well, if we take -3 and shift it up 1 space, that's going to be -2. And if we take 3 and shift it up 1 space, that's going to be 4. So the range of our function is going to be between -2 and 4. Now, I'm also going to graph this out compared to a regular cosine graph just to confirm these things that we just said about it. So in my calculator, I have in my y1 just a regular cosine of x graph, and then in my y2, I typed in that function that we were dealing with, so that 3 cosine of 2x minus pi plus 1. Before we graph this out, you do need to make sure that you are in radian mode. Graphing trig things needs to happen in radian mode. So when I hit graph, I get these two pictures. So that blue line is my original cosine curve. The red line is my new function that we were dealing with. So as far as the amplitude goes, we can see that our waves got taller. As far as the period, it's a shorter period, so our red graph is repeating itself more often than our blue graph. The domain, we can see that this graph extends to the left and the right forever and ever and ever. And then as far as the range, if we look at the lowest value and the highest value, the lowest value is down at -2, the highest value is up at 4. So we have graphically confirmed those things that we just came up with algebraically. In this example, we're going to be finding the frequency of a musical note. So we've got a computer that analyzed the pressure, displacement versus time for the wave produced by a tuning fork, and it gave the equation as y equals 0.6 sine of 2488.6x minus 2.832 plus 0.266. We want to use this to estimate the frequency of the note that was produced by the tuning fork. Frequency is directly related to the period of your function. For the period, we know that we take 2 pi and divide it by the b value, and then take the absolute value of that. That's how we find the period. The frequency is the reciprocal of that, so it's the b value divided by 2 pi. So in this case, as we're looking at our function, the b value is 2488.6, and we're supposed to divide that by 2 pi. Now when we do that, we're going to get approximately 396, and frequency is measured in hertz. And if you're a musical person, this happens to be the note G. That's going to be it for this video. Thanks for watching.